Hello, my name is Jeff Leonard and I'm an engineer here at Wright-Patterson Air Force Base. And I'm here with the Educational Outreach Department's Wizard of Wright program to talk to you about fire science and fire safety. The more we understand about fire science and the physics and chemistry of a fire, the more we understand about how to be safe from fire. Fire is the rapid oxidation or combustion of materials. It's an exothermic reaction that produces heat, light, and products of combustion. Now that's a very chemical, very specific definition, but we all know what fire is. It's when something burns. So let's get to some live fire exercises and see how things burn and how to prevent and extinguish fires. We're going to talk a little bit about the chemistry and physics of a fire and what we call the fire triangle. You need three parts to make a fire. You need to have fuel to burn, you need to have enough heat to ignite that fuel, and you need to have enough oxygen for the combustion to take place. So you remove any one of those elements, you take away the oxygen, or you take away the heat, lower the heat below the threshold, or you take away the actual fuel source and the fire goes out. So for instance, most people think that water suffocates a fire, taking away the oxygen, but that's not what really happens. Water cools a fire below the threshold for the fuel to continue to burn. A carbon dioxide or a CO2 extinguisher does take away the oxygen, as well as covering something with a blanket or putting a lid on a burning grease pan. That takes away the oxygen to extinguish the fire. In aircraft hangars, we use something called AFFF foam. It's a film-forming foam that puts out the fuel fires, because if you try to pour water on a gasoline fire, the gasoline just floats to the top and you can't put it out. So you have to suffocate a gasoline fire or a fuel fire with that foam, which will suffocate it. So because the air is the air in general, we don't vary that. What matters is having enough heat for the amount of fuel, and even more important than the amount of fuel is the size of the fuel. So for instance, if I take a match and I take a log, there we go. We all inherently kind of know that this match is not going to light this log on fire. All right, we just kind of feel that. But here's the trick. So we know that the sulfur on the end of this match has enough heat to burn a stick this big. It'll light this match on fire. And if it'll light this match on fire, it'll light this stick on fire. And if these two guys are burning, then they're thick enough to burn a stick this big. And if these two guys are burning, and if all of these guys are burning, that's enough heat. You ever heard the term add fuel to the fire, build the fire? Then these guys have enough heat to burn a stick the size of my finger. And once I start to burn that, pretty soon I can build up to something big enough to light something this big. So it's the amount of heat for the size of the fuel. Everybody knows that paper burns really easy. But if I take this newspaper and this lighter and I hold it below here, the paper didn't catch on fire, because for those few seconds, this paper's that big. It's 12 inches by 12 inches. All right, it's not paper thin. If I light an edge, it takes off right away, because it's the thickness of the material. All right, when I present the flame this direction, it's a big, wide present, and then here on the edge, it's very thin. Other examples, what I have here is a common household item. I don't know if you can recognize what this is. This is lint out of my dryer. All right, and dryer lint is made up of lots and lots of very fine particles, as thin as a hair, threads and lint from your dryer. But worse, it's in a nice big sheet. So if I was trying, if there was a spark flying, you know, the odds that it hits a thread is pretty small. But the odds that it hits a big piece like that, and even though this looks like a big solid piece, it's really a whole bunch of fine particles spread out in a pattern there. And so I have my sparker here, and if I simply aim it at the dryer lint, and there it goes. So you want to clean your dryer lint filter every time you do laundry, because as the dryer lint filter, first of all, any little spark will create a fire, and as the filter gets full and clogged, then the lint tends to bypass the filter and get into other parts of the dryer, and you don't want that getting in around the motor, around the heating element. That's how dryers start home fires. Now, as the size of the particle continues to get smaller and smaller, we need less and less of a spark and less heat to generate a fire. Farmers for years had issues with their grain silos. They would be pumping the silage into the silo. You see the big cylinders next to the farm. And as they were pumping the silage in, they would get a lot of dust. And dust of any kind of dust is very combustible. Even metal dust can be very combustible. And as the thresher was pumping it in, it would, if it hit the side of the silo and created a spark, they would get explosions. And we're going to try to simulate that grain silo explosion here. I have my miniature grain silo here, and it's going to be very tough for me to create the dust and then do the spark. So here's what I'm going to do. I have a candle inside that I will light, and that will be the heat ahead of time. Inside the silo, I have common table flour. I've already loaded inside, and I just have to kind of get the flour in position here, and then I put the candle in. That worked. How many people know what a flammable liquid is? A flammable liquid, some great examples are gasoline, kerosene, alcohol, are liquids that will have a flash point below 100 degrees Fahrenheit. If the flash point's above 100 degrees Fahrenheit, then we call it a combustible liquid. And certain liquids will burn once I preheat them, such as bacon grease. Most of your grease fires in your kitchens are really a combustible liquid because I had to heat it on the stove before it could catch fire. As it turns out, jet fuel is actually a combustible liquid, whereas gasoline for your car is a flammable liquid. As a safety feature, we've created jet fuel that has to be preheated before it can be burned in the engine. And that's just a safety feature. So here's a question for you to think about. Do flammable liquids burn? And the answer is no, they don't. What burns is the gas that evaporates off of the liquid. And the question is, when we say flash point at 100 degrees, does the liquid evaporate fast enough to support combustion with a spark or a small ignition source below 100 degrees, or do I have to heat it to get it to evaporate enough flammable gas in order to do that? Now, what I have here is some 70% isopropyl rubbing alcohol. It is slightly flammable. And to show you that alcohol or flammable liquids don't burn, okay, if the liquid burned, it would not be able to put out a match. We'd have a situation. But in order to show you that it's the vapors that burn, I'm going to pour a little bit of the alcohol into this small pan. So I have this small candle here, and it's got a little metal container around it. I'm going to set that in there as well. And the liquid is never going to reach the flame. But as the alcohol evaporates and this small pan fills with vapors, when the vapors get high enough, they should reach the flame and we should see something. Now this takes quite a while to happen. Alcohol doesn't evaporate actually all that fast. So I'm going to put it on my little coffee cup warmer here, which will cause that to happen hopefully within a minute here now. There it goes. Now it's going to be hard to see. It's a blue flame. I see a little bit of a yellow flame going there. All right, so that took less than a minute, and we're going to put this fire out by suffocating it. And we'll set this to the side because that pan's now a little hot to touch. So we talked about flour, and we used flour dust for the grain silo explosion. And any dust can be combustible, but organic dust and corn dust, things are very combustible. And in fact, corn chips are a great source of fuel if you're ever trying to light a fire while you're camping and you got your Fritos there with you. Okay, you got your corn, you got natural burnable stuff, and there's actually a little bit of oil in there from these guys, and these guys make a great source of fuel for helping start your campfire. And quick aside there, but we're talking about flammable liquids again. When I was a kid, I thought when you had a candle that the wax melted and ran down the candle and the string was burning. I didn't understand the concept of a wick. A wick is a string or a cloth that takes the fuel and pulls it up and gives it a place to evaporate and burn. Much like your kerosene lanterns have a wick. The wick doesn't burn up, it's bringing the kerosene up into the top where it evaporates and burns. Well, it turns out, since I now know a little bit more about fire than I did as a kid, that's what happens with a candle. The string burns a little bit, it melts the wax, then the wick sucks the liquid wax up into the wick, and at the top here in the flame, it then evaporates, and it's the wax vapors that are actually burning. And so we melt the wax, change it from a solid to a liquid, wick it up through the wick, and then evaporate it and burn it. And we can see this happen by the fact that the vapors that come off when I blow it out still have flammable wax vapors in them. So if I blow this out, I should be able to light those vapors for a second that still have that flammable vapor in it. So we're going to try this. I'm going to light this. Now, I'm not going to touch the wick. I'm going to be above there, and we should see the flame back trail to the wick. One more time. And that's those flammable vapors, the melted wax evaporating, because although the candle is a solid wax, it burns as a flammable liquid, which of course is not liquid at all. It's the vapors that come off from there. Now earlier we talked about the fact that the air is the air, and it's the amount of fuel for the size of the amount of heat for the size of the fuel. But what if we increase the oxygen content? We talked about the three legs: take away the oxygen, take away the fuel, take away the heat. If you add fuel, the fire gets bigger. If you add heat, the fire gets bigger. If you add oxygen, the fire gets bigger. So I have here some oxygen in this jar, relatively pure oxygen. Now, scuba divers use compressed air. They don't carry oxygen on their back, they carry compressed air because oxygen can be dangerous, and we're going to demonstrate that here in just a second. But astronauts can't carry enough air with them to get to the moon and back. Our air is about 23% oxygen, so if I carry pure oxygen, I need 1/4 the amount to breathe than I do if I'm carrying compressed air. So that's why astronauts use pure oxygen, because it takes up less space and less heat, less weight in their rocket ship. But pure oxygen is a serious issue. And in fact, on Apollo 1, when they had a little spark in one of the control panels inside the capsule, in the pure oxygen environment, which they were simulating because they were training in real conditions, the fire got out of control very quickly, and we lost all 3 astronauts. Now what I'm going to do here, I'm going to take this bamboo splint here, and I'm going to let the fire burn out. And if you can see that it's just glowing a little bit, it's just like a little spark. And when I put it into a pure oxygen environment, it bursts and it gets pretty rapid flame going. All right, I've used up all my oxygen in that one. So oxygen, although is not flammable, it causes any flame to increase greatly. When you're building a campfire and you tend to blow on it to keep it going, what you're trying to do is replace the oxygen that's being burned as faster than what it is being burned. And so we treat oxygen as a flammable. It is not, but because if it mixes with anything or during a fire, it will cause the fire to increase greatly. Quick aside on a fire, what to do if you're in a fire. If there's a fire, the first thing that you should do is, okay, yell fire. No, you need to evacuate and you need to let people around you know that there's a fire. Pull the fire alarm, yell fire, call 911, call the fire department. Now the good news is most fire alarm systems are tied to the fire department already, so pulling the alarm will evacuate the people as well as notify the fire department. And remember the acronym PASS, P-A-S-S. Pull the pin, aim A at the base of the fire, squeeze the handle and sweep back and forth. And when we say the base of the fire, we're talking not at the top of the flame, but at the bottom of the flame. Because what you think of it this way, you want to spray the fire extinguisher on the object that's on fire, not at the flames themselves. That's the easy way for me to remember. Spray it on the thing that's on fire. Thank you for your time and attention today, and I hope my demonstrations helped you learn some more about how fires start, how they burn, and how to put them out. Some key points to remember are a fire needs 3 main components: fuel, oxygen, and heat. The key to putting out a fire is removing one of those 3 factors from the equation. It's about the amount of heat for the size or diameter of the fuel. The smaller the fuel diameter, the less heat needed to create combustion or fire. From a fire safety standpoint, always clean your dryer lint filter, properly store your flammable liquids, and use the proper fire extinguisher for the type of fire if you choose to fight one. Remember, never pour water on a grease fire. The grease will only float to the top and the water will make things worse. If there's a fire in your building, always pull the fire alarm or contact the fire department by calling 911 first. Then evacuate the premises. If you choose to fight the fire, always leave yourself an exit. And remember the acronym PASS, P-A-S-S, when using a fire extinguisher. Pull the pin, aim at the base of the fire, squeeze the handle, and sweep back and forth. And remember, you want to spray the fire extinguisher on the item that's burning, not at the flames themselves. I hope you learned something about the science of fire and combustion, and I hope that you enjoyed this time we spent together. I know I did. Have a great day.